Our next speaker is Scott Gaudi to discuss the notional parameters, extensions, and auxiliary science of the Roman Galactic Bulge Time Domain Survey. So Scott, take it away.
All right. Hello, everyone. Oops. Sorry. All right. Does everyone see that? Okay. As my title says, I'm going to be talking about the notional parameters, extensions, and auxiliary science of the Roman Galactic Bulge Time Domain Survey. I want to acknowledge a lot of work done by the Roman Galactic Exoplanet Survey Science Investigation Team, which is now disbanded, but worked for many years on a lot of the stuff that I'm going to be talking about today. So we in the process of developing the science case for the Roman mission, we specified science requirements, as did all the large surveys. And we have 5 science requirements for the Bulge Time Domain Survey. That relate to basically the yield of planets that we expect, given some nominal assumptions about the planet population, or yield that we want in order to do the demographics that we want, as has been discussed before, in particular in Aparna's talk yesterday. And so these are related to both the total number of planets, or the total number of planets we can find, those that are below a certain mass, Earth mass, because those are going to be the most interest, as they are not detectable by any other method. The masses of the host stars that we can measure in the methods mentioned by Aparna and talks previous to mine today, the number of free-floating planets we can detect, and our ability to estimate eta Earth. So I won't specify what these are, but these are our science requirements as we define them, and this measures the success of the Bulge Time Domain Survey. So given those science requirements, then we can specify survey requirements that will allow us to meet those science requirements. And basically, given the properties of microlensing, its rarity, and the frequency of microlensing events towards the galactic bulge, we know that we have to monitor millions of bulge sources continuously on a timescale of roughly 10 minutes in order to be sensitive to Earth mass planets and below beyond the snow line. And that just comes from the event rate of microlensing events, the detection probability of Earth mass planets and lower mass planets, and the duration of the shortest features, which is set by the crossing time of the source, which is about 30 minutes. We need good but not exquisite photometry of a few percent. We need to resolve main sequence stars. That means we essentially have to go to space. And we need to resolve unrelated stars to measure the lens flux so that we can measure the lens masses as well. Again, I refer back to Aparna's talk yesterday. We also want long time baselines to measure the proper motion, as previously been discussed. So in terms of the parameters that we have to work with, there are some fixed parameters that were basically given to us by the nature of the telescope that we were gifted, and the engineering constraints we had in the camera size and the detector size. So these are basically the duration of bulge season, which is set by the field of regard of the telescope, slew and settle time, which depends on the moment of inertia of the telescope and the reaction wheels we have, detector size, et cetera. And so these are things we didn't really have much control over. And then there were things that we did have some control over. The microlensing filter was custom made for the Bulge Time Domain Survey. It spans roughly 1 to 2 microns. And of course, we can change the cadence, the number of fields, the field location, the exposure time, the total survey time, and choice of the bulge seasons, which of the ones we choose, and then the cadence of the secondary filters. And of course, not all of these are independent. For example, when you fix the cadence, the number of fields, and the number of fields, then the exposure time is basically set once you include the slew and settle time. So Matthew Penny worked on simulations that optimize these free parameters to try to maximize the yield of planets within a given range. And so what he came up with is basically what's been discussed many times, the notional Roman Galactic Exoplanet Survey. So you can think of this as one possible realization of the Bulge Time Domain Survey that can meet the science requirements that I've laid out before. So this notionally would be 7 fields of roughly total 2 square degrees. Again, the wide filter, 15-minute cadence, 50-second exposures, and then we would have observations every 6 hours or so in other filters, likely a bluer filter and a redder filter alternating. We would have 6 72 or 62-day seasons, TBD, and that ends up being a total of about 40,000 exposures in the wide filter, and 432 days spread over a 5-year mission. In terms of the statistical power of this survey and that yield, the yield we would come up with, has already been discussed by Aparna yesterday. So in terms of the statistical power of the survey for a sort of typical microlens source, we get a photon noise of about 1% per exposure. We get about a total of 1 billion photons for that F146 of 21st star. We saturated about 15th magnitude in that filter, and if you can average over many measurements, as Valerio discussed, then you can improve your statistics by the root of 40,000, or roughly 200. And then of course we're looking at a lot of stars because the bulge is very crowded. These are simulations of a typical bulge field that we would look at with Roman from space with Roman, and then from the ground on the right, a larger view and then a zoomed in view. Many stars down to 21st magnitude in this wide filter. We would have about 40 million stars, and we would detect about 30,000 microlensing events over the course of the 432 days with impact parameters less than 1. Okay, and in terms of the relative photometry and astrometric precision, this is just for photon noise. It's we don't know how well we can do what the systematic floor is going to be. We hope that we can achieve something close to the photon noise. So for 19th magnitude, that's 6 million stars, we get about 0.8% photometry and about 0.6 milliarc second precision per exposure. 21st is about 40 million stars, as I mentioned, 1% photometry and about 1 milliarc second or 1.5 milliarc second astrometric precision, again, per exposure. So with all of those parameters of the survey, obviously you can detect many microlensing events and detect many planets, but you can actually do a whole host of ancillary science as well. So one is that you can measure what I just call the compact object mass function. So this is free floating planets, brown dwarfs, stars, white dwarfs, neutron stars, and black holes. So these plots kind of show what the mass function towards the galactic bulge should look like here. So you see the brown dwarfs and stars. There's a peak here for white dwarfs, neutron stars, and black holes. This is actually the event rate weighted mass function you see. And so a significant fraction of our sources, our lenses, are going to be remnants like neutron stars and black holes, which we can then detect and identify using astrometric microlensing, as has been discussed. We're also sensitive to free floating planet, as Etienne discussed, and we would be sensitive to free floating planets with mass all the way down to that of Mars. And we would detect many dozens of such planets if they're common, 1 per star. So we would be able to measure that compact object mass function from planets to roughly 30 solar mass black holes, which is set by the observing window. So that's about 10 orders of magnitude in mass. With the photometry, Andy Gould showed that with the photometry that we get, while it's not exquisite, it's good. We can actually do astroseismology of giants. So giants have astroseismic signatures that are higher in amplitude and longer in time scale, which makes them amenable to detection with Roman. And so we would be able to measure the frequency of maximum power and the large frequency separation for about 10 to the 6 bright red giants in the survey fields. We would only measure mu max for the fainter stars. So that would give us masses and radii for all of these 1 million giants towards the galactic bulge. And of course, we would also get distances and parallax if we can get down to the photon noise. We're going to obviously be able to do resolved stellar populations. The Roman fields that we'll be looking at, the 2 square degrees, will be one of the deepest fields ever taken. And with that, we can reach all the way down the mass function, likely all the way to the hydrogen burning limit by combining all the exposures. We'll also be able to measure galactic structure, again, with the proper motion and parallax measurements, assuming we can get to the photon noise. We can measure proper motions and parallax for millions of bulge and disk stars. We'll get the multicolor photometry. And so with this data set over in all the filters, by just tiling the whole field occasionally in all filters, we would get, it would be relatively shallow, but still multicolor. And with that data set, it's in principle possible to disentangle effective temperature, crude metallicity, age, luminosity, and extinction for all of those stars. And so we can probe the bulge and disk population along the line of sight using this data set.
We have 2
And
minutes remaining, Scott.
thanks. Andy Gould also showed that the Bulge time domain survey will be sensitive to trans-Neptunian objects by basically shifting and doing image subtraction and then shift and adding along the tracks, expected tracks of the TNOs, all the way down to 30th magnitude in this wide filter. That corresponds to a diameter of about 10 kilometers. And it would be over an area of 17 square degrees, which is of course larger than the 2 square degrees because these objects are moving. And this data set would give you orbital elements to a few percent. And in addition, about 1,000 of these will actually occult bulge stars in the field of view. So you can get crude angular or radius measurements for these as well. Bennett and Rhee originally pointed out that we would detect many, many hot Jupiters with this survey, and this was explored in more detail by Benavente et al. And they showed that Roman would detect about 100,000 transiting planets with radii all the way down to 2 Earth radii. These are mainly hot and warm planets. Many of these can be confirmed by various methods, including measuring the secondary eclipse. So this is just a summary of some of the things we can do with the auxiliary science of the Roman time domain survey. And I would just briefly want to mention that, although the parameters of the survey are reasonably well constrained, given our desire to meet the science criteria, there is still some freedom. So we want to encourage the community to think about ways of tweaking the survey that can greatly increase the science without jeopardizing our ability to meet the science requirements. And some of these things include, for example, every once in a while, just going to the very galactic center and monitoring that at lower cadence. Because we're very close to that anyway. You could imagine periodic observations in all the filters, et cetera. And then you could also imagine extensions to the survey. And I won't go through these, but after the main survey is done, we may want to look for extensions to the survey, for example, doing very high cadence observations of a smaller area, which would enable you to be sensitive to much lower mass planets. And so this is kind of the path forward. I just want to throw these questions out to the community. What additional science can be extracted from the survey as is, and what additional science might be extracted from small tweaks in the survey strategy? And I encourage the community to think about very out-of-the-box ideas for extending the scientific grasp of the Bulge time domain survey. Some of these ideas may be unfeasible, but some of them may not. And with that, I'll take questions.
Thank you very much, Scott. And if I could pick up on your comment regarding the tweaking of the scheduling, many of these science areas could be enhanced by coordinating with other major surveys, as we heard at the beginning of this session. So, of course, coordinating 2 major facilities to observe the same part of the sky at the same time is quite complicated. So what scope do you think there is for coordinating between the major missions?
Well, so I mean, this is not something I've worked a lot on, and you've worked on, and so has Etienne and other people as well, Matthew Penny. I think that there's a lot of coordination, in particular with Ruben and Roman, particularly because we're not going to get all of the. We only have these short seasons, whereas Ruben can look at the microlensing events for most of the bulge time, and so that'll be especially important for measuring parallax of longer timescale events. Which is going to be hard to measure with the extant Romans data. And of course, Etienne explained the synergies with Euclid and with JWST. You could imagine also following up events to try to actually measure the text spectra of bright lens events, which I think is an interesting possibility that needs to be explored.
Absolutely, thank you. And I see we have another question from Kiash Lede, and my apologies if I'm mispronouncing that. The current microlensing fields avoid the central galactic plane where most of the stars are. Are the microlensing requirements sufficiently affected by moving the fields closer to the plane?
Right, so this is a great question. So as you move closer to the plane, the number density of stars does increase, but your extinction also increases. So the number density of stars above a given magnitude isn't necessarily much larger. Your event rate does increase more rapidly than your extinction because it basically goes as the number density squared, particularly for bulge lensing. We did a preliminary UCURT survey to try to see what the event rate is in the near infrared at these lower L fields, absolute value L fields. We found the event rate is indeed higher, but because of the high extinction, it's actually very difficult to pin down the properties of the source, which is required to measure the masses of the lenses and planets. And so our preliminary idea is that we don't want to go too close to the plane, but this needs to be revisited, and that in particular would be done by the PRIME survey, which is being led by Takahiro Sumi, the new infrared telescope that is going to be monitoring the galactic center in the infrared to measure microlensing event rates and other science.
Thank you. And with that, we are at the end of the first part of our session. So Scott, thank you very much once again. And thank you to all of the speakers in the first section.